So in this video, we want to take a look at something called the Euclidean algorithm. We're going to begin this section with a little theorem, and we'll prove it, and then we'll explore what the algorithm itself says. So this theorem states that if a and b are natural numbers, and r equals a mod b, then the GCD of a and b is equal to the GCD of b and r. So let's see what it would look like if we went to prove this. So theorem. So if a and b are natural numbers and r is equal to a mod b, then the GCD of a and b is equivalent to the GCD of b and r. So prove. So by the quotient remainder theorem, there exists Q and R such that A equals BQ plus R for R between 0 and B. Let's let C be a common divisor for A and B. Then C divides B times Q. Since C divides A and C divides BQ, then C divides the difference between them, meaning C will divide the difference between A and BQ. Which implies then that C will divide R. Thus, C is a common divisor of B and R. Conversely, if C is a common divisor of B and R, then C divides BQ and C divides BQ plus R, or C divides A. Hence, C is a common divisor of A and B. Therefore, the GCD of A and B is equal to the GCD of B and R. Now, what the Euclidean algorithm is This is a very old algorithm that is used to find the greatest common divisor of two integers. I have kind of a makeout right here, a blueprint of what the code would be if one wanted to program and find the GCD of two non-negative integers. So the input I would have to input in two non-negative integers a and b, and obviously the output is the greatest common divisor of these two. So this is kind of what the algorithm says. Okay, we're going to let a be the larger of the integers. So whichever one is larger, I'm going to call it a. The smaller one, I'm going to call it b. If for some reason a is less than b, then we're going to swap them. So a is the largest one. Okay, now this is what this while loop says. It's saying while b is not equal to 0, so as long as b is not equal to 0, okay, we're going to compute a mod b. Okay, we're going to compute a mod b and store that as r. And then we're going to set a equal to b and b equal to r, and then return a. And so the idea is this will loop around until we get a b value of 0, and so it will then return what the greatest common divisor is of my two integers. So let's see if we can't use the Euclidean algorithm to find the GCD of these two integers. So let's take a look at 64 and 24. So in this case, we're going to say that m is 64 and n is 24. So we first do 64 mod 24. So the bigger number mod the smaller number. In my calculator, give me just a second to pull up this TI-84. In my TI-84, I programmed in a modular arithmetic program. Okay, and so the first value a is what I'm calling m, so 64. And the second value b is 24. So 64 mod 24 is 16. Okay, so the 16 is still bigger than 0, so we're going to repeat the process again. Okay? And so now we're going to go 24 mod 16. So what was the n value now becomes the m value, and what was the remainder now becomes the n value, or the smaller of the two. And so now let's compute 24 mod 16. And so I'll run this through again. So 24 mod 16 is 8. Okay, and now let's do it one more time. So now we're going to go 16 mod 8. So the 16 now becomes the m, and the remainder now becomes the n. And let's compute 16 mod 8. So 16 mod 8, and this should be evident right here. 16 mod 8 is 0. The remainder upon division is 0. So the GCD of m and n in this case, or the GCD of 64 and 24, is this 8. Let's do another one. So let's compute the GCD of 825 and 315. Okay, so first we need to do 825 mod 315. So 825 mod 315 is 195. And now we can see how we're just going to repeat the process. 315 mod 195. So 120. 195 mod 120. And now some of these we can start to kind of do in our head. 120 just goes into 195. That's one time with 75 left over. And we're just going to continue. So 120 mod 75. Well, 75 goes in 121 time with 45 left over. If I go 75 mod 45, 45 goes into 75 once with 30 left over. 45 mod 30. 30 goes into 45 once with 15 left over. And now if we go 30 mod 15, notice we get a 0. So hence, the GCD of 825 and 315 is this 15 right here. Okay, for the sake of time, we're going to skip this next example and take a look at one more theorem. So what this theorem states is that if A and B are natural numbers, A and B both not 0, then there exist integers S and T such that the GCD of A and B is equal to SA plus TB. In words, this is saying the greatest common divisor of two numbers, A and B, can be written as a linear combination. Okay, linear combination is this SA plus TB. A linear combination using A and B as integer coefficients of S and T. So let's take a look at this next example. So let's use Euclidean algorithm to find the GCD of 270 and 192. So let's go 270 mod 192. And that is 78. Now, I want us to notice that I can write this 78, okay, as 1 times 270 minus 1 times 192. Now, we haven't gotten a 0 out for our remainder, so we need to do the algorithm again. So let's go 192 mod 78. Okay, this would go in there 2 times with the remainder of 36. So this means that I can write 36 as 1 times 192 minus 2 times 78. Okay? So this equals 36, and this first guy right here equals 78. Okay. Okay, well, yet again, let's go 78 mod 36. 78 mod 36 would be 2 with 6 left over. So I can then write this as 1 times 78 minus 2 times 36, and that's how I can write a 6. Okay, one more time. So 36 mod 6 is 0. Okay, so the GCD of 270 and 192 is 6. Okay, so what we want to do now is we wish to write this GCD, this 6, as a linear combination of 270 and 192. That is, find integers s and t such that the GCD of 270 and 192 equals 270 times s plus 192 times t. So let's see how we might do that. Okay, so the GCD of 270 and 192 is going to equal 270 times some number s plus 192 times some number t. Okay? Now, let's recall that we just found that the GCD of 270 and 192 is in fact 6. So we're now going to find s and t such that 6 equals 270s plus 192t. Okay. Well, and this is why we did what we did just a second ago back here in the notes with this PDF, where I wrote each of these out as the product of two integers and then taking the difference between them. So I want to write 6 as 270s plus 192t. Well, here's the idea. 6 equals, how can I write this 270? Well, I can write this 270, okay, as 1 times 78 minus 2 times 36. Because notice, what we're doing more or less is we are going to work our way back up this chain more or less, because I can write 6, if we notice this third line right here, I can write 6 as 1 times 78 minus 2 times 36. Well, how can I write 36? Well, take a look at line number 2. So in this case, I can then say that this is equal to 1 times 78 minus 2 times 36. Well, what was my linear combination for 36? 36 was this 1 times 92 minus 2 times 78. So 1 times 192 minus 2 times 78. Okay. Well, if I clean this up a little bit, okay, this is 1 times 78, and I can distribute this minus 2 in, and then write this as minus 2 times 1, which is 2, times 192, and then let's see here, we would get minus 4 times 78, which then would be 5 times 78 minus 2 times 192. Okay, sorry, that needs to be a plus right here. The minus 2 times that minus 2 is a plus. Okay. So what do we have? I have 1 copy of 78, 4 copies of 78, so 5 copies of 78, minus 2 copies of 192. Okay. Well, if we continue just a little bit more, I can write this as 5. Here, I'll copy down what we just had. 5 copies of 78 minus 2 copies of 192 so this would equal 5 times, okay, well, how can I write this 78? If I look back here into the notes, I can write this 78 as 1 copy of 270 minus 1 copy of 192. So let's write that in. So this is 1 copy of 270 minus 1 copy of 192. That's how I can write this 78 minus 2 times 192. Okay, well, let's distribute this 5 in. So 5 times 1 is 5. So 5 copies of 270. Subtract. 5 times 1 is 5 copies of 192 minus 2 copies of 192. That's 5 copies of 270 minus 7 copies of 192. Thus, 6 equals the GCD of 270 and 192, which I can write as this linear combination. I can write it as 5 times 270 subtract 7 times 192, where this 5 is my S, and this -7 is my T. And just to check, let's actually punch in this linear combination and let's see what we get. And we should get the GCD of 270 and 192. So when I punch this linear combination in, it should output a 6. So let's see here, 5 times 270. So 5 copies of 270, subtract 7 copies of 192. Hopefully it equals 6. It does. So we found our integers s and t to where I can write this GCD as a linear combination of the two. And that will close the door on the Euclidean algorithm.